Hi, everyone. First of all, thanks to the organizer for giving us this opportunity to report. It took us nearly 2 months to participate in this VATEX video captioning challenge, and we finally won the first place in both Chinese and English races. Our team members including Zhu Xinxin, Guo Longteng, Liu Wei, and Liu Jing, who come from Institute of Automation, Chinese Academy of Science, Yao Peng, who come from University of Science and Technology, Beijing, and Lu Shichen, who come from Wuhan University. Next, we will introduce our working method in detail. Video captioning aims at describing the video content with natural language. To promote the progress in video captioning, the VATEX Captioning Challenge is held. VATEX dataset in this challenge contains video covering 600 human activities, and each video paired with 10 English and 10 Chinese diverse captioning. The fundamental challenge of this task is to accurately recognize the activities in the video clip and depict them with high-quality, diverse captions. An example is shown in figure. Our baseline video captioning model mistakes the activity jet skiing and surfing, and man falls off is ignored because this action is too fast to be noticed. Another challenge in this task is the vast diversity of the captions. Still, we take figure for example. The ground truth captions for this specific video differ a lot either in the captioning content or in the captioning length. We identified 3 crucial factors to solve above problems, namely multi-view features, hybrid reward, and diverse ensemble. Based on our method of VATEX 2090 challenge, we achieved significant improvements this year with more advanced model architectures, combination careful hyperparameters tuning. Specifically, multi-view features extracted by different backbone models aims to provide more comprehensive and discriminative video representations, including appearance and motion features. The hybrid reward method directly optimized a linear combination of Cedar, Metro, Rouge, and Blue scores during the reinforcement learning stage, which we found performs significantly better than solely optimization, one of them. Furthermore, by using diverse ensemble of 2 state-of-the-art caption frameworks and different video features as input, we achieve Cedar scores of 59.5 and 81.4 on the test Chinese and test English splits of the VATEX dataset respectively. To better extract the thematic features of the video, we refer to a variety of video feature extraction methods to extract more thematic features. We hope to enhance the model's understanding of the different thematic information of the videos by combining multiple features. In this work, we mainly consider the motion and appearance features. Motion features operate mainly on the temporal dimension, which tells what activities the person or objects in the video are involved in. Our motion feature extraction networks include the I3D features, provided by the video team, the non-local methods, and the TSM model. To better extract the video features, we use the strategy of randomly cropping video frames and randomly selecting partial videos. Appearance feature operate on the spatial dimension, which tells what objects are shown in the video. To fully capture the appearance of each key object, we use an object detector to detect key objects in the keyframe of each clip. Specifically, we use faster RCN in conjunction with a stronger ResNet 152 backbone to extract object features for the keyframe. The detector is pre-trained on the visual genome dataset for better feature representations. The object features are input to obtain the appearance feature for each keyframe. The resulting appearance feature in conjunction with the corresponding motion feature of that clip serve as inputs to the captioning model. Our captioning model including two types of framework: linear based on LSTM and transformer based on self-attention. Based on compared to last year's challenge, we used a more powerful linear model, which can achieve better performance than the top-down model. Linear is an attention block that just came up in CVPR 2020. The block can easily replace traditional attention block in LSTM or transformer architecture. Linear block exploits both the spatial and channel-wise bilinear attention distribution to capture the second-order interactions between the input single-modal or multi-modal features, selectively capitalizing on visual information or perform multimodal reasoning. As shown in figure, linear model is a stack of linear attention blocks, which are leveraged in image encoder to encode the region-level features with the higher encoder intramodal interactions in between, leading to a set of enhanced region-level and image-level features. Depending on the enhanced visual features, linear attention block is further adopted in sentence decoder to perform multimodal reasoning. This encourages the exploration of high-order intermodal interactions between visual content and natural sentence to boost sentence generation. For the linear model setting, the dimension of the bilinear query key representations and transformed bilinear feature in linear attention block is set as 1024 and 512, respectively. The hidden layer size in LSTM decoder is set as 1024. We stack 4 linear attention blocks in the encoder, and the sentence decoder is equipped with 1 linear attention block. The hidden layer size in LSTM decoder is set as 1024. We set the maximum iteration as 70 epochs for the first learning rate stage, since low-rank bilinear pooling may lead to slow convergence rate. And then we train the model for another 35 epochs. The transformer is another standard encoder-decoder framework, largely different from the LSTM-based framework, and the advanced the state-of-the-art on various natural language processing tasks. It is a stack of multi-head attention substantially, using the self-attention mechanism to compute hidden representations of two arbitrary position inputs. Disintegrate a whole video into a series of clip features. Video captioning task can be adjusted to fit the transformer framework. Inspired by this insight, we transfer transformer architecture into video captioning task. The setting in the transformer model is similar to the trilinear model. The latent dimension in the self-attention and the feed-forward network are 1024 and 4096. The number of the head is 16, and the latent dimension for each head is 64. The number of attention blocks in the encoder and decoder are 1. All the transformer models are treated as the following setting. The base learning rate is set to 0.0001 and increase to 0.0003 every epoch. After 6 epochs, the learning rate is decayed by 50% every 3 epochs. The learning training stage lasts for 15 epochs, and the second training stage lasts for 10 epochs. Reinforcement learning can further promote the performance of the model, and it has been proved that the optimization for the Cedar criterion can advance other criterion indirectly. Cedar, Metro, Roach, and Blue are the criterion for the caption quality requested by the official VATEX website. The partial optimization for some criterions can result in better performance on the corresponding criterions. In this task, we find that using a hybrid reward, such as a linear combination of different metric scores, can result in a better overall resource. We adopt the common practice of the ensemble methods, such as average ensemble and weighted ensemble. The experimental results demonstrated that weighted ensemble methods has little improvement over average ensemble, so we solely choose the former strategy. Our single models mainly belong to two different architectures, trilinear and transformer, and each type of model is reserved by 4 strategies. For example, the models with different initialized size, the models treated with different settings such as the learning rate or schedule sampling probabilities, the models with different visual features as input. Finally, we integrate all those models by average method. In order to better improve the final performance, we use the model ensemble strategy in the final test stage to fuse all the models treated by different hyperparameters. Since there are models that use data from the validation site, we only list the results of the test site. We show the trilinear results and trilinear plus transformer results in the table 1. The final result of the VATEX Chinese combines the prediction results of 10 trilinear models and 8 transformer models. At the same time, we show the results of the VATEX English in the official test site. The final result combines 15 trilinear models and 17 transformer models. That's all. Thank you.